Warahmatullahi wabarakatuh and salam sejahtera. Today we will discuss chapter 4, vapor power cycle. So the content of the chapter is 4.1, basic steam power plant, 4.2, the Rankine cycle, 4.3, improving performance, Rankine reheat cycle, and 4.4, improving performance in Rankine regenerative cycle, which is not included in this topic. So for the objective, first thing first, it is to analyze vapor power cycle in which the working fluid is alternately vaporized and condensed. Second, investigate ways to modify the basic Rankine vapor power cycle to increase thermal efficiency and to analyze the reheat vapor power cycle. Okay, let us revisit the Carnot vapor cycle. This is the component involving Carnot power cycle. We have pump, we have boiler, we have turbine, and we have condenser. And this is a TS diagram. So 122 is processed in a boiler, and we can see from the TS diagram this is isothermal. So this is an isothermal. Here we have Q in, which is heat has been added in a boiler. From state 2 to 3, this is expansion process in a turbine, and we have W dot out. And this process is in expansion process. 3 to 4, if you can see here, it happens in condenser. Here, the heat will be removed out. Okay, and this process happen in isothermal process. And 4 to 1 is adiabatic compression in pump or in compressor, and we have W dot in here. Okay, the problem with the Carnot cycle is to achieve isothermal heat transfer is very difficult because it needs very large heat exchanger and long time. So this is the isothermal process at 1 to 2 and 3 to 4. Okay. Next, the problem with the Carnot cycle is here. If you can see here, the process occurs in saturated mixture. So we know in saturated mixture, we have liquid and gas. And we know that the turbine consists of blades made from aluminium. Okay, so if we have liquid here, so it means that it will cause the blade to damage. Okay, and it cause a corrosion. And for 4 to 1, this is adiabatic compression in compressor. So we see here that in compressor we have two phase, that is mixture and saturated liquids, which is impractical. Okay, therefore we have to modify this Carnot cycle. Okay, so to modify this Carnot cycle, we rearrange the state. So this is state 1 at the inlet of the pump, state 2 at the inlet of boiler, state 3 at the inlet of turbine, and state 4 is inlet of the condenser. So we rearrange the S diagram, and we have this cycle. 1 to 2 is adiabatic expansion, adiabatic compression. 2 to 3 is heat addition. 3 to 4 is expansion in turbine. 4 to 1 is heat rejection. So the impractical associated with Carnot cycle are eliminated with superheating the steam in the boiler. So if you can see here, in boiler, okay, the heating is limited at T2. But we modify in Rankine cycle, we reheat the liquid up until superheated here in state 3. Okay, next what happened is this in condenser we have two phase, which is mixture and liquid, and this is not practical, and we modify this problem with we condense the mixture completely in a condenser so that the liquid that will going out from the condenser will be in saturated liquid. Okay, so this cycle, the modification of Carnot cycle, we call it as a Rankine cycle. Rankine cycle, Rankine is a scientist, so this is Rankine cycle, and this is ideal cycle for power plant. Okay, so if you can see from this figure, okay, we have this component in here, okay, in here. So from this cycle, it will produce W dot out, which is will operate the generator, and the generator will produce electricity, and the electricity will convey all the electrical to factories, stores, and home. Okay, now we go to the Rankine cycle. Alright, this is Rankine cycle, TS diagram, and this is the component that involved in the Rankine cycle. We have pump, we have boiler, we have turbine, and we have condenser. So the ideal Rankine cycle consists of 4 processes, 1, 2, 3, and 4. Okay, for process 1 to 2, this is isentropic compression in a pump. Okay, isentropic compression in a pump. Okay, so if you still remember the definition of isentropic is Q is equal 0 and it is reversible. Okay, 2 to 3, this is happen in a boiler, so there will be heat addition. So the heat addition occur in constant pressure. Okay, so 2 to 3 is constant pressure heat addition. 2 to 3 to 4, okay, this is happen in a turbine, and it is isentropic expansion. And 4 to 1 is a constant pressure heat rejection. So this is heat addition and this is heat rejection. Okay.